Hello, my name is Dr. Duška Kleut, and I would like to thank the organizers for inviting me to speak at the 8th IEEE Symposium on Wireless Technology and Applications. And my topic for today's talk will be key factors in the electromagnetic interference shielding by graphene-based composites. I will now present the outline of this presentation. I will first introduce you to our project, then some basic details about graphene, its uses in electromagnetic shieldings, and the composites we are making for this purpose, and I will present some conclusions. First, I would like to introduce you to our Green Shield project, which is a project which received funding from the European Union Horizon Europe Coordination and Support Action. And some of the goals we had in writing this project. We had concerns about the pollution caused by electromagnetic waves, who have intensively grown in both telecommunication and electronic industry, and also electromagnetic interference, which may present a negative impact on both on electrical devices and human health. So thin, flexible materials like fabrics and layered materials that can absorb electromagnetic waves are in high demand. And our project was created to bring innovation in the field of shielding materials by exploring new graphene-based nanomaterials as a protective barrier. Our project has 4 consortium members, including institutions in Germany, France, and Slovenia. And since it is the widening action project, it has 2 main goals. One is to increase the scientific excellence of the consortium by addressing scientific questions with economic and industrial impacts, and also to improve the administrative skills of the coordinator institution, which is our Institute Vinča for Nuclear Sciences in Belgrade, Serbia. I would also like to thank Dr. Kamel Haddadi from Institute of Electronics and Microelectronics at the University of Lille, who is the keynote speaker at this conference as well, for inviting us to be part of a special session in March 2023 conference, the International Conference on Manipulation, Automation, and Robotics at Small Scales, in October 2023 in Abu Dhabi, where we had the pleasure to meet Dr. Zuhair Ismail Khan, Dr. Setia Malina, and Hia Abrahim from the Microwave Research Institute in Mara University of Technology in Malaysia, and also the other keynote speaker at this conference, Dr. Mohammed Abu Kusa from the Khalifa University in Abu Dhabi. And this was a very special occasion for us, and we were very happy to establish the collaboration, which led to us having this talk here today for you. I'm sure you know a little bit about graphene, which is a form of carbon consisting of planar sheets which are one atom thick, and the atoms are arranged in a honeycomb-shaped lattice. And this picture shows some of its most prominent characteristic. It's a very thin atomic thickness material who has great electromobility and strength, toughness, stiffness, and the high surface area, impermeability, and electrical resistivity, as well as good thermal conductivity and transparency. What we have been doing is trying to obtain graphene in bulk in order to use it to create nanomaterial composites able to be used as materials for electromagnetic shielding. The issue with creating large-scale graphene is that it's difficult to obtain in bulk, especially in uniform shapes and sizes and characteristics. What most people do when trying to produce large-scale graphene is they create reduced graphene oxide, commonly chemically obtained by reducing graphene oxide. These materials, due to their structure, both graphene and graphene oxide and reduced graphene oxide, possess many properties different from their bulk ancestor graphite. But thanks to their structure, they are both chemically stable and resistive to humidity, acidic conditions, which makes them a better alternative for shielding materials than metals. And their lightweight, elasticity, and mechanical strength have been studied and determined that they are able to block the propagation of low-frequency electromagnetic waves, and so they are a possible candidates for application in electromagnetic shielding. Some of the literature that we have been studying in preparation for our project exploitation and creating the graphene oxide films and freestanding films and reduced graphene oxide freestanding films that we were able to produce. We studied a lot of literature, and some of the conclusions that both the literature and our preliminary results have led to is that graphene is able to absorb electromagnetic waves, and the reduced form is more efficient in shielding than the graphene oxide. The thickness plays a very important role, and the shielding effects increase with the graphene layer number. And also the defect-free graphene, which is highly conductive, is very efficient in shielding, but better efficiency can be also achieved by increasing layer number. And here in the picture on the right, you can see one of the results from 2012, which shows the mechanisms of interference shielding for monolayer and multi-layer graphene. And also in incorporation of electron-rich atoms in graphene sheets or doping can also eventually add improvements in the electrical conductivity as well as electromagnetic shielding of graphene-based materials. So in our research, we have produced some freestanding graphene-based materials, both graphene oxide and reduced graphene oxide. And then we developed a setup for electromagnetic characterization for our samples, and it is based on microwave coaxial probing. It was done in Lille at IMN, and it consists of VNA interfaced with dedicated coaxial probing setups, planar metallic structures with coaxial sensing apertures, and what we did was we put material under test in cellulose sheets sandwiched between two metallic structures, and then we measured as parameters. We also did various kind of different setups, both with our partners in Germany and in Lille. This is just one of the methods that we used. And these are the composite materials that we created using graphene and silver nanowires in our aim to produce the best possible material to have the highest level of electromagnetic shielding. We are planning to create both composites of inorganic and organic materials with graphene, and this is one of the materials that we already published research on, consisting of graphene oxide and silver nanowires, and we reported about 5 decibel decrease in transmission coefficient at about 5 gigahertz for this kind of composite. The next step in our research is to include the materials that we produced, both the graphene oxide and reduced graphene oxide, as well as the composites, inorganic composites of graphene and silver nanowires, into some kind of polymers and composites with organic polymer materials to improve their flexibility and transparency as well for further use, since they are very fragile and brittle. So we have studied a lot of researchers and results that did this kind of composites, and PMMA is one of the composites that shows great promise. And in this study by Pavlu, they showed that in the terahertz range, such composites have shielding efficiency of up to 25 decibels at 5 micrometer thicknesses. and we have created some preliminary composites of various concentrations of graphene and graphene oxide in PMMA, which display the ease of manipulation and characteristics of this composite material. And to conclude, here we presented the main structural, morphological, and electromagnetic shielding properties of graphene produced by a large-scale approach. We displayed an example of the results of electromagnetic shielding of various composites as well as composites with PMMA. And thanks to the good electromagnetic shielding of graphene oxide and reduced graphene oxide, they're considered promising candidates for different kinds of applications. There is still pretty much to explore in order to obtain the best possible results regarding different kinds of composites with these materials and sample preparation techniques. And also we have to develop good methodologies for shielding efficiency measurements to achieve reproducibility, repeatability, and reliability of our results. I would like to thank my co-authors on this publication, Dr. Kamel Haddadi, Mohamed Sebash, Christoph Boyaval, and Svetlana Ivanovic, and I would like to thank you for your attention.